Earlier this week, I finished motor control setup for my automatic lawnmower project, and I started looking into a good obstacle avoidance system that can be fast enough to deliver quick reactions, that will be able to reliably work outside in high vibration and high humidity conditions. After some research, I found that the most common obstacle avoidance solution for robotic applications is this ultrasonic HCSR04 sensor, but I quickly realized that it probably won't survive all the grass clippings and moisture getting inside, so I decided against it. Laser sensors like this TF Mini LiDAR have a very narrow field of view, which makes them not a good fit for my application. After all, I decided that standard parking sensor should probably satisfy all my needs. However, there weren't any available that I could easily plug into Raspberry Pi port and work with. So I decided to go with cheap aftermarket parking sensors you could easily get off eBay for like $15 delivered to your door. I was able to successfully tap into the data bus and read the signals. However, the signals were very inconsistent with distance readings and fluctuating a lot without any apparent reason. So I decided to get this 8 sensor version that promises precise detection up to a centimeter right here on the box. Packaging includes installation manual, 8 ultrasonic sensors, good informative display module, and a main control module where everything plugs into. I'm gonna make my test setup out of this simple shipping box and install front and back sensors on opposite sides like they would be in case of typical car installation. Okay, so I put this thing where I have less obstacles and it's not constantly beeping at me. And right now I can test and see how accurate this thing is on a distance. So these are my rear sensors. I'm gonna try to put an obstacle here. So let me put it somewhere here. So it shows that I have about a meter before it hits that obstacle. So let's take a look how accurate this thing is. And we got about 3 feet, which is pretty close. And I would say this thing is right on. I wasn't expecting much out of it. The original unit that I bought that only had 4 sensors in it was by far less accurate than this thing is. So I should say this is probably better designed and built. So we're gonna take it apart and take a look inside and see what's in there and what we can do about hacking into this. Okay, so it looks very similar to the one that I've used for a force sensor setup. So just to compare, let me show that one to you. This was the one that I used for a force sensor setup, and as you can see, it's very similar to this in its design. So I would say tapping into the output of the digital logic of this thing should be just as simple as it was with the force sensor one. The only difference that I see between them, frankly, is probably going to be the power wire, because this one takes one additional wire, which is that brake wire. This one was only 3-pin power, so it didn't have that additional feature. But we're not going to need it anyways, so let's take a look at what kind of signals we can see on a scope. Okay, so I'm touching pin number 2, and this pin, just like on the original 4 sensor module, is our signal wire. As you can see, these packets of data, they're being transferred on that pin number 2. We see 5 volt on pin number 3, and looks like nothing on pin number 4. But yeah, pin number 2 is definitely our signal wire, and we have pulses of 5 volts, as you can see on a scope. So that's good. That looks pretty much just like the original force sensor module, and it shouldn't be too much different as far as tapping into the internal logic of it. So I decided to use the wire provided to me by the manufacturer and solder them right on the back of these pins right here, so I have simultaneous output to the display unit, and I can analyze it at the same time using the scope or my Logic Analyzer. Okay, so now I soldered this pin headers. It's much easier to tap with my scope. So let's see again if we're gonna get the same results here. Okay, and we see that we have this steady signal on our scope. That's going to be our signal and data to the display unit, and that's the data that we're going to need to get our distances and resolution. Let's plug into the Logic Analyzer, and we'll have a better picture now. So let's take a look. I'm gonna start software for the Logic Analyzer. Okay, now that everything is connected, we should be ready to start sampling. This is what all the data packets looks like on a timeline, and this is the individual data packet. As you can see, every data packet starts with a longer pulse followed by a sequence of shorter pulses, where the longer pulse is our starting pulse and all the short pulses are representing zeros and ones. If I measure the starting pulse, it seems to be like it's exactly 1 millisecond long, and the duration between the pulses, between the data packets, is actually 35 milliseconds. And it stays very consistent. Okay, I've just noticed I was sampling it with the incorrect voltage settings, so I'm going to resample it with the correct settings this time and see if something changed. And it looks to be the same. We still have the duration between the pulses equal to 35 milliseconds, and the starting pulse is still 1 millisecond long. So no changes there. At this point, I should be ready to start mapping my pulses to data bits and see what kind of data I'm getting in each individual packet. Okay, so here I'm not going to count the starting pulse, just the pulses that represent the data bits. And what I expect is that after 8 packets, I should start seeing the same series of bits in address section of the packet. This is the address of each individual sensor, which should be the first 8 bits. Okay, so weird thing just happened here while I was decoding. The thing is that the packet number 7 that I just decoded is exactly the same as packet number 1, which means that our module is just reporting 6 sensors and not 8. So I'm going to continue on decoding to see if I see the same thing. And indeed, the packet number 13 that I got here is the same exact one as the packet number 1, which means that they start to repeat itself after 6 data packets, which means we're not getting all 8 sensors reported. And I'm not exactly sure if there's a coding issue with the module or it's supposed to be like that, but I went ahead and I tested the front sensors individually, and indeed the middle 2 sensors not registering any movement at all. It's just a left and the right one that are sensing distance, but not the middle one. So that explains why we only get in 6 data packets in a row, which it's not going to be a big deal for me, because I wasn't actually expecting that I'm going to be using all 8 sensors anyways. I just needed a higher precision, so for me it's going to work regardless. I wrote down the durations of data pulses, as I'll need those later. Okay, so it's time for some Arduino coding. All we're gonna need for reading our input pulses from the parking sensor module is one digital input pin. So we'll set it to pin number 7 on Arduino Duo. We're also gonna need some sort of a data structure to hold our bits. So 32-bit integer will work. So we're gonna set it to unsigned integer and we'll store our packet in it. Next, we're gonna need to store our sensor address and the sensor value, both of which are just 8 bits. So we're gonna allocate a byte for each one of them. We're also gonna need one variable to store the measured duration of the pulses coming in. So we'll use unsigned long for that, as this number can be pretty big measured in microseconds. Next, we can initialize the input pin and the serial port, as it's gonna be used to output the test data. I will now add logic for detecting the starting pulse and add it to the infinite loop section of the sketch. This is now ready to be uploaded into the Arduino board. Okay, so this is my setup. I connected my ground and a signal wire to Arduino pin 7 and ground pin, and now I should be able to get my signals read. Let's see. So once I open the serial terminal, I expect to see those start pulses coming in. So let's see, and it looks like they come in. I'm going to clear the output, and you can see that there's a bunch of them coming in. As I said earlier, they come in every 35 milliseconds, so it's quite a bit of data. All that is left now is add some logic for detecting data bits and pre-print them into the serial output. So right now, once I open up the console, I should be able to see the sensor addresses along with their values, and that's exactly what we see. I should probably comment out the start and pulse output not to have that much garbage, but these values, they have an 8-bit resolution, so they take values from 0 to 255. So that's our max values, and these values, they are in centimeters. So I'm gonna take the reading value from one of these rear sensors and compare it to the actual output, and as you can see, it matches exactly. So that's 207 and 207 on a display. So the next thing, I will need to make a couple boxes for the sensors and 3D print them so they will match my front bumper for the lawnmower. And they came out great, actually. So all I have left to do is probably upload the sketch into some smaller board, something like Arduino Mini, something with a USB port that I can use to connect with my Raspberry Pi driving unit. So that's it. Thanks for watching and have a great day.